Good morning, lads and ladies. Welcome back to Calc 1. Let me get things set up on this end, and we can start moving forwards. Here we are. Okay. So today I want to talk with you guys a little bit about something that is near and dear to my heart. It's a special perspective on the derivative and differentiation. It's not a technically challenging section, but it is a conceptually challenging section. And I want you to sort of think along with me and think of this as our gentle introduction to this week, which is going to be our first week of like applications, all applications. Oh, that's right. This isn't connected yet. Come here. Come on. I don't know why this thing insists on disconnecting even if it hasn't been shut down. There we go. All right. So here's the deal. Today we're going to talk about section 3.10. It's a personal pet peeve of mine. If a textbook author chooses the numbering system, like, something dot something else for chapters and sections, to let the number of sections go beyond 10, because then it's like it really doesn't make sense as a decimal. But I'm sure you all know what I mean. Today's the 22nd. Yeah. Oh. So today we're going to talk about linear approximation. Differentials. This is the aforementioned section 3.10. So in a slightly more grown-up math class, we would talk about, particularly a slightly more grown-up geometry class, at what's called differential geometry, which is the language that Einstein used to describe general relativity, and the language that mathematicians use to describe, what we call manifolds, which are like other kind of mathematical spaces where things are still smooth enough that you can do calculus. In the language of differential geometry, we say a function is differentiable if it can be approximated nicely by a linear function at every point in its domain. And then the derivative is said to be the linear function that does the approximating the best. So you kind of take your function, pick one point, and then ask, of all the lines that go through that point, which one does the best job of approximating our function near that point? And that's how we define the derivative in a lot of other contexts, but most notably in differential geometry. So the things that we're going to be talking about here, linear approximation specifically, is intimately connected to the derivative and this other way of interpreting or even defining the derivative in terms of geometry. And then differentials, these are, your book treats these differently than I'm going to treat these. Your book kind of connects differentials to linear approximation in a way that I don't fully approve of. It abuses the notation and does all sorts of things that make mathematicians cringe. So when it comes to the differential stuff, I'm just going to be having you learn the notation, because one forms and zero forms are important. You need to learn how to calculate differentials for the sake of U substitution, which is something we're going to be talking about after we talk about integrals. So let's get to it. These are the two things for today. Let's talk about linear approximation. First. And I'm going to begin by drawing a graph here. Not any particular graph, just a kind of generic graph. All right, so we're gonna say that this is the graph of f of x. And of course, this is my x-axis. And I'm gonna, pick an x value in here somewhere. I'll call it, how about this one? Call it A. And that means the point on the graph right here is a comma f of a. Right, and I'm going to draw on a tangent line, and of course that a comma f of a there, that's my point of tangency. Try to do a good job sketching this tangent line. So we should all be very comfortable with the idea of what a tangent line is by now. This is not a new thing for us. You take your favorite differentiable function and your favorite number a in its domain, then the slope of this line is the derivative of f evaluated at a, and the point is a comma f of a. So you can come up with the formula for this tangent line without too much trouble, right? This is something that it was a problem on our first test. It's something that we know how to do. We've done it in many homeworks at this point. So we should be very comfy with it. I want you to imagine for just a second that I say, okay, this line has to go through that point. I'm going to pretend the pen is the line. The line has to go through that point. If I choose any other slope, then that line kind of moves away from the graph of f of x faster than this purple line here, right? That's the big idea that I was talking about. So the tangent line is the line that best approximates our function near x equals a. Let's go ahead and write that down. The tangent line to f of x at x equals a is the line that best approximates. And I'll come back and talk about what exactly I mean by best approximates. Best approximates f of x near x equals a. What I mean by that is, if you take some other nearby point, right? Let me call this B over here. Why not? How about C? Then up here on the graph is the point C comma f of C. That's the point on the graph of the function f of x. Imagine f of a is easy to compute, but f of c is very hard to compute. Like maybe this is a function involving square roots and a is like 4. So okay, I can take the square root of 4, no problem. But this is 5. The square root of 5, that's fucked up. That's an irrational number. I don't know how to compute it by hand very well. So imagine for whatever reason, I know this y value, and I want to know, but cannot easily compute this y value. The purple line is pretty close to the black graph, right? It's close enough that I might consider this an acceptable approximation here. So whatever this is, the x value here is definitely c. And what I'm going to do is I'm going to call the y value here L of c. The difference between f of c and L of c is small. So by best approximates, I mean minimizes this distance. C near A. And we would say here that L of C is really, really close to F of C. And there's nothing special about C. More generally, if X is reasonably close to A, then L of X will be reasonably close to F of X. What is L of X? L of X is the tangent line. Okay. So let me back up here a little bit and give you guys some time to write things down and get it all clear in your notes. This is everything that's going on with linear approximation. Linear approximation is about trying to approximate the y value on the graph of some function. Maybe it's hard to compute, maybe we're just doing it for fun. The way we do that is by finding the tangent line, which we call L of X, L for linearization or linear line, you know, L. L of X at X equals A. And then you can plug the number, the X value in that you wanted to approximate the Y value of. So if I wanted to know F of 5, but F of 5 is hard to compute, I plug 5 into the linearization. I plug 5 into the tangent line. The nice thing is that because the tangent line is always a linear function, it's very easy to plug into. So we'll never have a hard time plugging into the purple. We can have a very hard time plugging into the black sometimes. And by best approximates, I mean, if you picked any other line, it has to go through this point. If it's going to do a good job of approximating f of x at A, then I mean, it has to agree with f of x at A. But imagine I picked any other slope. If I move this down, if I change the slope like that, then the gap on this side is getting larger, right? And you might say, oh, well, why don't you move this up a little bit? That would give me a better approximation over here. And that's true, but that would make things worse on this side. If I move this up to close the gap on that side, the gap on this side widens. So the slope of this line is the one that keeps the gap smallest on both sides. And that is the tangent line. So in slightly more grown-up math classes, the derivative is defined to be the linear function that best approximates your function at that point. And so here we would say that the derivative and the tangent line are kind of equivalent concepts. And that's something that we've seen before, right? If you want to find the tangent line, the first thing you need to do is find the derivative. So let me show you what this looks like in practice. I'm going to use it to do precisely what we said. I'm going to compute some square roots. Anybody need more time writing these things down? Okay. Oh, I got shit on that side already. Right, so let's use tangent line summation to estimate the square root of, let's go with the square root of 37. Whoop, you guys can't see that, can you? All right. With the function function f of x equals square root of x and base point x equals 36. So here's the idea. This is funny, by the way. This guy, well, I forget his name, but he was all over TV when I was a little kid. There were all these ads. I don't know if you guys, probably too old. Funny stuff. Vice did a little profile on him. Anyway, kind of graphically, here's what's going on. I am going to zoom out a little bit here. Maybe a little bit more. All right. So I know right here on the graph, there's this point, 36, 6. Red, give them a label. All right. I don't know what the point over here is at 37. I have no idea what the square root of 37 is. It's not a nice number. 37 is prime, so his square root is irrational. So I'm looking to find the y value on the graph right here, right at 37, wherever that is, 37. But that's a tricky thing to do. So instead, I'm going to find the tangent line to this function at this point, and then I'm going to find the y value on that tangent line. So let me show you what that looks like. First, find the tangent line to f of x at x equals 36. So my point is 36, comma, f of 36. And f of 36, if you plug 36 into f of x, you get 6. This is 36, comma 6. And my slope is going to be f primed of 36. So I calculate f primed of x, which is the derivative of the square root function, which is the derivative of x to the 1/2, which is 1/2 x to the -1/2, which is 1/2 square roots of x. So f primed of 36, that's 1/2 times the square root of 36. Square root of 36 is 6, so that's 1/2 times 6, which is 1/12. So my tangent line is y minus y0, which is 6, equals m, which is 1/12, times x minus x0, which is 36. Now we solve this for y. So if I do that, I'll get y equals 1/12 times x minus 36 plus 6.
Why is there a 2 next to the square root of 36?
Sorry?
I said, why is there a 2 next to the square root of 36 in the slope?
Well, because the derivative is 1 over 2 times the square root of x. Right? So we calculated f prime of x, and then we plugged in 36. So if f prime of x is 1 over 2 times the square root of x, then f prime of 36 is 1 over 2 times the square root of 36.
Oh, I see. Thank you.
Yeah,
Thank
so
you. Sorry.
I did this first, and then I
Yeah.
came back here and plugged it in. So now this thing is my tangent line, and this is what we call L of x. So I would say L of x is 1/12 times x minus 36 plus 6. And if I wanted to know the square root of any number that's close to 36, I could plug it into this function and get a reasonably good approximation out. So I'm going to go ahead and graph this guy now in Desmos. And then we'll use it to do the approximations. So just so you can see the picture. Here it is. And you see that as long as I keep my x value close to 36, the green and the red are very, very close to each other, right? Not so shabby. So in particular, if I want to know, what is this point right here, the purple point, right? I don't actually have a clue what that y value is. Desmos is telling me right now that it's about 6.083, but I don't know that. All I know is that, you know, it's the y value on there is the square root of 37. If I want to know what that is, the square root of 37, I know that that is f of 37, because f of x is the square root of x. That's the function I'm messing around with. And that's hard to compute. But I know it should be really, really close to the y value on the graph of the linear function L of x. And the miracle is that since this is a linear function, it's very easy to plug into. You'll never have to take a square root. You'll never have to have any sines or cosines or anything weird. It's just a linear function. So this is 1/12 times 37 minus 36 plus 6. Okay, well, that's 1/12 times 1 plus 6, which is, well, let's see, if I have 6 as a ratio over 12, 6 is multiplied by 12, 12 times 6. And we could just write this as 6 and 1/12, or 1/12 plus 6 if we wanted to, but let's do it like this. 6 times 10 is 60, plus 6 times 2 is 72, so this would be 73 over 12. Yeah, I'm doing that arithmetic right. It's still a little bit early for me. So I claim that this number, 73 over 12, should be real fucking close to the square root of 37. Let's see. All right, just for fun, let's calculate the square root of 30. Oh, sorry, 30. I don't know this calculator very well. Okay, 6.082762553, blah, 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 blah. Keep that tucked in your pocket. And now let's take 73 and divide by 12. 6.083. So look how close these are. First decimal is correct, second decimal is correct, third place is correct. The fourth place, if you were to round to 3 decimal places, if you were to round this to the nearest thousandth, you would round this guy up to this guy. We are off here by like 5/10,000ths. We are off here by very, very little. And when your calculator calculates the square root of 37, it's doing something very similar to what I did here. It's doing almost the exact same thing. It uses 1 or 2 more terms.
Why don't we just plug in 37?
What's that?
So why don't we just plug in 37 right at the beginning?
Well, we can. I mean, so that if you plug 37 into this, you get the exact value of the square root of 37. But do you know what that is? I don't. It's an irrational number. It's hard to compute. That's the point, is that the square root of 37, this is hard to compute. But this is a rational number. It's a fraction made up of whole numbers. It's easy to compute. So you have to pretend like you don't have a calculator, right? That's the idea. This is important in that this is how your calculator works, right? If we didn't have like tools handed to us from the gods for figuring out square roots, we would need to come up with those tools. This is how we come up with those tools. So this is actually how your calculator is figuring it out. It uses something called a Taylor expansion, which has a few more terms in it, but the kind of core idea here is that this thing is very hard to calculate by hand. But this stuff is very easy to calculate by hand. So similarly, you can imagine somebody, there was this silly movie when I was a little kid where some lady in a shop, like some kid goes into a shop and some lady is like, tell me the square root of blah, 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 and you'll get some sort of, I don't know, special deal, abacus, some sort of treat. If you had to do that, this is how you do it, right? You set up a linear function to approximate the square root function at a nearby, easy to work with point, and then you plug in whatever you want. So I didn't know what the square root of 37 was when we started this. But now I know that the square root of 37 is real fucking close to 73/12. Real fucking close. And this number, 73/12, I didn't need a calculator at any point to figure that out, right? We were able to get this all on our own by coming up with this linear function and then plugging 37 into that linear function. That gave me this without ever using a calculator. We used the calculator at the end there to just kind of verify that, yeah, this is indeed very, very close to what the actual value is. This is like 6.027 and 6.0827, and this is like 6.082 or whatever it was, you know, they're exceptionally close. So what did we have here? Here's the exact value returned by the calculator. And here's the thing that we figured out purely by hand. And you see how close these are. This down here would be plenty good. If you were building a bridge, and for whatever reason, when you were building the bridge, you needed to know what the square root of 37 is, this would do the job. This would be plenty good. You guys feel like you're understanding kind of the point here and the mechanics? Are there any questions you'd like to ask about what we just did? So the point is that this number is real fucking hard to calculate, right? The square root of 37, real hard to calculate because 37 is a prime. If I didn't have a calculator, all I could tell you is that, well, it's probably pretty close to 6 because the square root of 36 is 6. But using this linearization, which I was able to find by hand, I can get a very, very good approximation for the square root of 37. So being able to give accurate approximations to things that are hard to calculate is one of the big goals of mathematics. This is something engineers need all the time, right? Engineers don't care that pi is irrational. They care, how to build something circularly. So they don't need pi exactly. They just need a good approximation for pi. Engineers, when they're building a bridge, might need to make something the square root of 37 feet long. And if it's not accurate, then the bridge might collapse. Well, if they need to make something that's the square root of 37 feet long, they can make it 73/12, and that will be good enough. And the point is, even though today we have calculators that can help us with these things, we need somebody to program the damn calculator. And this is what's going on inside the calculator. So it's all about approximation. It's about getting some number that is very close to the actual y value on the graph f of x equals square root x at x equals 37. This would be the exact y value. This is my approximation. And we know that this is really, really close to this. So anywhere you needed this, you could swap this in instead. And kind of the picture that you should have in your heads is this one, where you've got your linear function being very, very close to your actual function, as long as you stay reasonably close to the base point. Right? So imagine I wanted the square root of, what's another number we don't know the square root of? I have no idea what the square root of 46 is, right? What else can we do with this? So here's my function L of x. What if I wanted, let's do something else close by. Let's do something like the square root of 35. I know that the square root of 35 would be f of 35. So that should be really close to L of 35, which is exactly 1/12 times 35 minus 36 plus 6. That's 1/12 times -1, so -1/12 plus 6, which is going to be 71/12. So I don't know what the square root of 35 is, right? 35 is not a perfect square. It's a product of two primes. It's a semi-prime. The square root of 35, according to the calculator, is 5.91. The square root of 35, according to my linear approximation, is 5.916. Look, see, really fucking close. What else do you want to do? We can check, or let's see how far we have to go away before this starts getting bad. The square root of 40, this would be f of 40, should be pretty close to L of 40, which is 1/12 times 40 minus 36 plus 6. Well, 40 minus 36, that's 4. So this is 4/12 plus 6. 4/12 is 1/3. And 6 is 18/3. This is 19/3. So I claim that the square root of 40 should be pretty close to 19/3. Here's 19/3. 6.3333. And here's the square root of 40. Not too fucking bad, right? So if you want the first few digits of the square root of some number, as long as that number is reasonably close to 36, you can plug it into this function, L of x. And if you wanted the square root of some other number that's not reasonably close to 36, you just have to construct the linearization at some nearby point. I use this to calculate the square root of 2, usually when I go through this lecture, because root 2 is a famously irrational number, but so are all these other square roots. So is this helping at all? Are we feeling a little bit more comfy with what's going on here? The idea is that you can approximate the y values on these graphs, which are normally very hard to calculate. Any other questions or comments? What are we doing? Why are we doing it? How's it working? Anything like that? Any questions about any of the individual steps here? So the good news is mechanically, it's not much very new, right? You just find the tangent line and then solve it for y. You don't even have to distribute, right? Just add this shit over, and that's your linearization. Okay. So there will be a problem on exam 2 where I say calculate the linearization for such and such function at such and such point. This is what you need to give me there. So let's go ahead and kind of wrap this up a little bit. The linearization of f of x at x equals a is the function L of x, which is f primed of a times x minus a plus f of a, as long as x is reasonably close to a, then L of x is very close to f of x. The term linearization should have components that you recognize, right? Like linear. Linear means is a line. And this ation, like, right, the ization part of the word here is like turning it into, right? So we're turning f into a linear function as best as we can. That's what linearization means. The linearization, L of x, is the linear function that best approximates f of x near a. So if there's a formula you need to remember, it's this thing. All right, you gotta remember this. And it's not hard to remember because it's just the tangent line solved for y. But if you want to remember it on its own, that's the formula. The way I always do this is just find the tangent line and then solve for y, because that's kind of the thing that we've been doing. So let's try one more example here, and then I will show you the notation for. Show you the differentials. Sure. Here, while you're writing, I will refresh my coffee.
Hey, Professor, I had a quick question about something.
Mm-hmm.
I just want to know, did you happen to get my email I sent yesterday?
I think I saw it, Robert, but I haven't had a chance to read it yet. I did see that I got something from you, but I have not read it yet.
Okay.
Yeah, I will. I'll be clearing out my inbox a little bit later today. I've got some more grading to do. Like, I know your exam and a couple other people who took a makeup test. So I'll be, if it's pertaining to that, I'll be getting that very, very soon. But
It's more on the last week's homework. I was just having some difficulties with it.
Oh, I see. Okay, yeah, I'll take a look at that as soon as I can. If you want to come by the office hour this afternoon, we can talk there too.
Appreciate it.
All right. I'm going to go ahead and move on now. Fabrice, was there something else that you wanted to ask about here, or did we need to go back or anything, or was it just this? Just need more time to write this? You good? All right. So let's take a look at one more example here, and then I'll talk about differentials. Differentials. All right, so here's the picture. There's the formula. They use this to calculate some other square roots, like the square root of 3.98 and the square root of 4.05. It's the same shit. Those things I won't be holding you too tight to. But I would like, I would like to do one more approximation problem like this. Linearization of this. Verifying this. On differentials. Well, maybe not. There really isn't a whole lot to do. Find linear approximations. This function is calculate this. And that's all the same sort of shit. Yeah, okay. Never mind. We'll just talk about differentials. There are really only a few problems in the book, and I want to save those for your homework. So let's go ahead and change gears slightly to talk about differentials. This is going to go very quickly. So the differentials, there are ways of thinking about these things that connect them to linear approximations. Differentials are expressions like dy, dx, du, dz, etc., which stand for infinitesimal changes in the variable y, x, u, z, and so on. So dy is like a teeny tiny change in y. These infinitesimal means like very, very, very small. Specifically, it means infinitely small. Like so small, they're not even numbers. Smaller than any positive number, but technically bigger than 0. Yeah, so the word here is infinitesimal. infinitesimal, infinitesimal, which means infinitely small. So teeny, 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 tiny changes in y, x, u, and z, respectively. This is how Newton thought about these things and how Leibniz thought about these things. But again, today we have a much more sophisticated way of thinking about these. We call them one-forms, differential forms, one-forms. And again, this is coming down to the language of differential geometry. So we think of these as being either infinitesimals or differential forms. In either cases, they're not numbers, right? They're definitely not numbers. So we can't like multiply, divide, any of those, like the algebra of the real numbers doesn't apply to these things. because they're either infinitesimal, which means they're too small, or they're differential forms, which means something entirely different. We don't even fucking know what that means. If you want to know, take a differential geometry class. In any case, they're definitely not numbers. They're their own thing. Later, when we talk about integrals, we will need some way of relating an infinitely small change in x to an infinitely small change in y, because we're going to be making what are called coordinate changes. We're going to be changing our coordinate systems, doing what are called substitutions. And as you change from one coordinate system to another, it's important to think about how that affects the gap between any 2 points on the graph. And it turns out that differentials are exactly how you do that. For me in this class, all I'm going to require you to do is to learn how to calculate differentials symbolically. So we won't be doing any approximation with differentials. And if you talk with friends who take this class, they might do that. If you read the book, you'll see that in there. But technically, they're doing all sorts of bad shit when they do that. They're using the notation incorrectly. So we're going to stick just to the linearization for approximations. That is a valid thing. And when it comes to talking about differentials, all you need to learn is the definition, but you do need to learn it. If y is equal to f of x, then dy is equal to f primed of x times dx. That's literally all I need you to learn about differentials. Easy as pie, right? And you can think of this as kind of being similar to saying dy dx is equal to f primed of x. And some teachers say, okay, well, if dy dx is f primed of x, then just multiply both sides by dx and you get this. That's what I mean when I say abusing notation. Because these things are so small, they aren't even numbers, we can't multiply or divide by them. Like it doesn't work that way. They're not that kind of object. There is this thing called non-standard analysis, where people talk about things called hyper-real numbers. And in that setting, you can define an algebra where you can multiply and divide by things like dy and dx. But really, it's not correct, and they're not real numbers. So this is all I need you to get good at doing here, is calculating differentials like this. So for example, if y is equal to x squared, find dy. This is what a problem might look like. This is a very simple one. Well, dy here would be the derivative of x squared, which is 2x times dx. That's it. Or if u is equal to e to the 2x, find du. Well, if I want to find du, I need to differentiate. So du should be equal to the derivative of this function times dx. What's the derivative of e to the 2x?
E to the 2x times 2.
Mm-hmm. Yeah, very good. I'll bring the 2 up front. So this is 2e to the 2x. That's the derivative. And then I just have a dx at the end. See, this isn't too tough. We're just taking derivatives, but we're doing it in a slightly different notation. And that's what I mean when I say the differentials portion here. We're just going to learn the notation. That's all we need.
What's the difference between like just dy and then dy dx? And that may be what you're talking about, but
it is, yeah. So that's where this gets a little bit hairy. Dy dx is a function. Dy dx is f primed of x. Dy on its own is an infinitesimally small change in y that you can find by taking the derivative and then multiplying by the infinitesimally small change in x. So imagine you you want to know like what the hell is dy. We know that dy and dx are both infinitely small. But if you want to kind of imagine it a little bit, you can say, okay, well, let's imagine dx, instead of being infinitely small, is just really small, like 0.001. Then dy would be f primed times 0.001. It's going to be a very, very small number that comes from taking your derivative and multiplying by some other very, very, very small number. Really what it is, I'm going to scare you a little bit here. Hang on to your pants. Don't write any of this down. It's a differential form. Basically, mathematicians, when they started trying to think very carefully about what calculus is and how it can be applied to three-dimensional and higher spaces, started studying algebras built up out of derivatives. So the thing like f of x dx here, which is pretty similar to what we're looking at here, is what we call a one form or a differential form. It's a linear map from a complicated function space down onto the real numbers. It's a function that takes as its input other functions and spits out numbers. These sort of things are what we need to study in order to develop a theory of integration in a place called a manifold. The real numbers, the real line, like the number line, is a manifold. And what we do in this class is develop calculus on that manifold. That is the simplest of all possible manifolds. But if you're Einstein or any sort of differential geometer like Riemann, you want to develop calculus in three-dimensional space, or you want to develop calculus in four-dimensional space-time, then it turns out you need to start building special sorts of algebras on those spaces. The way you build the algebras you need on those spaces to do calculus on those spaces is by thinking about these things not as infinitesimally small changes in x or infinitesimally small changes in y, but by thinking about them as differential forms, which are kind of these purely abstract concepts that say, I take in a function and I spit out a real number. And that lets you map functions on the manifold down to functions on regular real numbers. And there we can apply the calculus we know. It's a fairly complicated concept. It's not a super easy thing to understand or explain. But the simplest way I can say it is that this is a differential form. And what it does, it takes in the function f of x, and it spits out another function that we could call dy, or we could call f prime of x dx, which when you plug in a number gives you a number. In other words, it's what's called a linear functional. All of this is stuff that you'll learn about if you take a class called linear algebra. You'll learn what linear functionals are, and it all kind of lives in this domain of differential geometry and functional analysis. For us, it's just a notation. You can think of dy dx as f prime of x, right? That's our normal derivative. And if you kind of multiply both sides by dx, you get this expression. Later down the line, we're going to be looking at objects like this right here. This is called an integral, and it's the thing that measures the area under f of x from a to b. In order to work with integrals like these, we need to be comfortable working with, you see the thing inside there, it looks a lot like this differential form. We need to know how to work with these, but we only need to know how to work with them symbolically. We need to know how to like move them around and substitute one for another. So for us right now, the dy, you can think of it as being very, very similar to y prime, right? It's kind of like the derivative of y, but it hasn't identified who's taken with respect to. So if it makes it easier to think of this as dy dx is f prime, and then you just multiply by dx, that's okay, because it will yield the right result. But for now, I just want you guys to practice going from something like this to something like this. So the mechanics should be clear. The concept here is unfortunately a little bit harder to understand, but basically what we're saying is, if I wanted to go from some coordinate system where X is the variable and change to some other coordinate system where Y is the variable, what I would be doing is making a substitution. So if I have some function of X and I want to switch to having that function have its inside variable as Y, I could choose to substitute Y equals X squared. And if I did that, then that will stretch out the coordinate axis. And this guy right down here tells me how much the coordinate axis gets stretched out. For example, so here, don't write the orange. Suppose I have something like sine of X squared. I can substitute Y equals X squared, and this becomes sine of Y, right? Sine of X squared would turn into the sine of Y if Y is X squared. I know what the graph of sine Y looks like. I have no idea what the graph of sine X squared looks like. So if I graph this, and I know how this substitution stretches the x-axis, then I could tell you stuff about the original function here, specifically like how much area was underneath it. That's kind of where we're going. And right now, I know that all sounds very scary. So don't worry about any of the orange. Don't write down any of the orange. Just focus on the calculations here for now and trust that the understanding of this shit will come with time. After we've talked more about derivatives and introduced integrals and shown you how integrals measure area, then I'll be able to explain a little bit what the move is here. I know that's not super appealing, but I hope that helps a little bit with the conceptual question. If you want, I'll show you one more thing. If you want, I think I have this in my Calc 2's notes here. Yeah, good question, Trevor. The answer is no. It is correct to say we should not be trying to solve equations with dx's or dy's, because all of the algebra processes we use to solve equations, those are for real numbers. Dx and dy are not real numbers. So those algebra processes really don't apply to them. Here's a really good explanation I give to my Calc 2 kids, and I'll be sharing with you guys at the end of the semester. So here we have the function 2x e to the x squared. And here we have the function 2 root u e to the u. What the man has done in going from this graph to this graph is made the substitution u equals x squared. If you want to know how much area was underneath the original function, you could find how much area is underneath the new function. But, and it's a big, big but, the density changes. When you make the substitution u equals x squared, it kind of squishes together the x-axis down here. You see these guys getting squished together, and it stretches out the x-axis up here. So you have to count the area back here a little bit less, and you have to count the area up here a little bit more because it's been squished together here and stretched out here. dy, or in this case it would be du, measures how much stretching or squishing is going on. So I'll paste this into chat. This will be relevant down the road. And if you want to try and understand a little bit more about differential forms, that link would be, it's the best resource I've found for students at our level so far. And I've been looking for years. But again, for now, I just need you guys to get comfy going from this to this, or going from this to this. So let's do one more bit of practice here. I'll hold for just a second. Anybody who needed to write down. Don't write down the orange, but please do write down the black. Trevor's question in chat is really, really good. In fact, he's getting exactly at why I don't cover this the way the book covers it. Because the book does treat dx and dy as variables that you can like play with and solve, and that's totally not true. So no, we should not be trying to solve equations that have dx's or dy's in them, or certainly at least not manipulating the dx's or dy's themselves, because they are not numbers. They don't have a set value. All right, we'll do one more of these sort of calculations. Remember, this is the only thing I need you to really get comfy with here, is how to calculate this from this, or how to calculate this from this. So find dz if z is equal to x cubed plus 3x. Well, how do we do it? I just take derivative, right? I take the derivative over here and I slap a dx on. So dz is equal to the derivative of this function, which is 3x squared plus 3. And I put that all in parentheses, and I slap on a dx. The parentheses are important here. This is why I'm showing these last few examples. We'll do one more. Find dw if w is equal to the natural log of x plus, let's fuck shit up a little bit. How about the inverse tangent of x? This will be our last little bit of differential calculation. So the derivative of ln x is what?
One over x.
Good. I have a 1 over x from that, plus from this. Now what's the derivative of the inverse tangent of x?
1 over x squared plus 1.
Very good. Yeah, this is something we learned last week, right? When we talked about implicit differentiation. So dw is all of this times dx. And again, this is all I need you guys to pick up from the section on differentials, how to go from here to here, how to go from here to here. So if you're comfy with that, and you are comfy with using the function L of x to approximate f of x, then you are good with all of section 3.10. That's the whole thing. Easy section, right? Okay, I'm going to leave it here for today, guys. That's all I have for you. On Wednesday, we're going to talk about finding maxes and mins on a graph. Those come from horizontal tangent lines. So I invite you to read section 4.1 in the textbook. So I still have about 15 minutes. Maybe I'll go ahead and introduce that. That way we're not just wasting time. So this is the end of section 3.10, and I'll do a quick intro to section 4.1 on academic. So imagine I have a function f of x like this. You should remember from your pre-calculus and algebra classes before that this point up here is called a maximum. Specifically, it's a local max. And the point down here is called a minimum. Let's be. So we would say the language we would use here is we would say that f of x has a local max at x equals a. And the max value is f of a, whatever that y value is. Similarly here, we could say f of x has a local min at x equals b, and the min value is whatever that y value is, f of b. So the language is important, and let's start there. If I ask you where is the max or where is the min, I'm asking for the x value. The location of the min and the location of the max, the location of any feature on a graph, we're always asking for the x value. And if I ask you what is the max, well, what is the max? The max is the y value, f of a. If I had to ask you what is the min value, that would be f of b, whatever the y value is there. So where is something? That's always the x value. What is something? That's always the y value. I ask you, what do you notice about these graphs at those points? What's special about these points? Besides this being a local max and this being a local min, what can you tell me about the tangent line to f of x here or here?
It's going to be a horizontal line.
Very good. The tangent line here is definitely horizontal. Right? If you imagine your tangent lines at both these points, they're definitely horizontal. Here. Okay. So we have, my art is bad, but yeah, we have a horizontal tangent. Okay, so what does that tell me about the derivative? This means that f primed of a, the derivative at a, which is the slope of the tangent line there, has to be 0. And that f primed of b, which is the slope of the tangent line at b, also has to be 0. So a cool way to go hunting for mins and maxes is to take the derivative and then figure out where that thing is 0. If you have a nice smooth function with a max at x equals a, then it must be true that the derivative there is 0. And similarly, if you have a nice smooth function with a min at x equals b, then it must be true that the derivative there is 0. The converse, it turns out, is not true, and this is called Fermat's theorem. This will be the last thing I show you today. And maybe I'll give you a definition after this too. So this says, if f of x is differentiable at x equals a and has a local min or max at x equals a, then f primed of a must be 0. So a good way to hunt for mins and maxes, as long as you know your function is differentiable, is to hunt for places where the derivative is 0. And then there's a definition here that I'll give you, and this will genuinely be the last thing for today. I'll let you go after this. Any number c in the domain of f such that f primed of c is equal to 0, or f primed of c is undefined, shit, we're gonna need a little bit more space here, is called a critical number for f of x. All right. So this is where I will pick it up on Wednesday, right from here. So we have Fermat's theorem, which tells us that if you have a min or a max at some number, then the derivative must be 0 there. And you have this definition of a critical number. It says a critical number is any number in the domain of your function such that the derivative of your function is either 0 or undefined. So you can guess how we're going to find mins and maxes. We're going to first find critical numbers, then apply Fermat's theorem to deduce that those are places where we might have mins or maxes, and then we're going to check the results. This is Fermat, F-E-R-M-A-T, Fermat. He's a Frenchman. So this is a theorem named after him. There's actually many theorems named after him, but F-E-R-M-A-T. Alrighty, gang, this is where I'm going to leave us for today. There will be a new homework opening up in just a little bit, and the new homework is going to have linear approximation, differentials, mins and maxes, and maybe one more little topic, depending on whether I think we'll get there by the end of the week. But this is the bulk of the material for this week's linear approximation, differentials, and finding mins and maxes. We'll talk more about mins and maxes on Wednesday, and then if there's time, I'll talk a little bit more about something else on Friday. But we will have to see how fast we move through this. Any burning questions for me before I let you go?
I know like we had our exam, like our last exam later than it was scheduled on the syllabus. Will this one be pushed back or will it still be before spring break?
So I would like to get our second exam in before spring break. Let me take a look at the syllabus real quick, see how far off we are. The big goal for me, I want to make sure you have exam 2 graded before the withdrawal deadline. So you have like 2 exams to make your decision based on. And I know that it's usually better to have exams before spring break rather than after them because people have this way of forgetting things. Now, spring break this year is the 2nd week of March. So we are here, related rates, linear approximation, min max problems. So what do we still have to do? We still have to do 4.1. 4.3, 4.4, 4.5, and 4.7. I could push 4.7 to being on exam 2. That's an option, have applied optimization be on the next test. But it really makes the most sense to have it on this one. I'm not sure. It will depend. It'll depend on how quickly we move through these sections. L'Hôpital's rule can be easy, can be hard, depends on how deep we go there. And then the graphing stuff, we've done a little bit of this already. But you're gonna need some practice on this. This is a hard section. So I'm thinking we have at least 1 week's worth of material left before we're ready for exam 2, which means to get exam 2 done before the 8th would be a real challenge. Probably, I don't have a good answer for you yet. I will try to get you a good answer to that question by Wednesday. If we're going to have exam 2 before spring break, that means we're going to have it next Friday. And that's not impossible, but it would mean I'd have to bump some stuff that more naturally belongs on exam 2 to exam 3. So probably what I'll do is I'll end up holding a vote. I'll let you guys decide whether you want to do exam 2 before or after the break. If you do it before the break, then we're going to have to move some stuff that would normally be on exam 2 down here to being on exam 3. And that's a little bit weird because it kind of splits up the material in a strange way. But it would also avoid this thing where you have an exam right after coming back from break, which I know nobody wants. So let me get a feel for how quickly we're moving through this week's material. I'll hold a vote on Friday and let you guys decide whether you want the exam next Friday or you want it after break, okay?
Thank you.
Of course, yeah. Any other questions or comments? Alrighty, then you guys have a lovely afternoon, rest of your morning, whatever. And if you want to talk about problems, you're having trouble with anything, just come see me in office hours, send me an email. If you've already sent me an email, haven't gotten a response yet, please be patient. I'm working on it. Just got a lot of stuff to do right now. I promise I will get to it. If you need something more urgently, come by office hours. Take care.